We present Learning to Drive via Asymmetric Self-Play. Large-scale data is crucial for learning realistic and capable driving policies. However, most driving data collected in the real world is repetitive and uninteresting. Upsampling curated scenarios can help with the data imbalance, but is ultimately limited to the existing set of logs. Naively scaling to collect more long-tail scenarios is expensive and can be unsafe. In this work, we ask, how can we continue to scale training data without relying solely on real-world collection? One existing approach is to allow policies to explore novel states using algorithms like reinforcement learning and simulation. However, because other actors exhibit nominal behavior, the resulting scenarios can still be uninteresting. Another approach is to hand-design challenging synthetic scenarios, but this can be difficult to scale, and the realism may be lacking. Adversarial optimization can be used to automatically generate challenging scenarios, but it's unclear how to make sure that these are actually useful for training. To address these shortcomings, we design an asymmetric self-play mechanism where challenging, solvable, and realistic scenarios automatically emerge from interactions between a teacher and student. Specifically, the teacher's objective is to generate realistic scenarios where the student fails, while also trying to ensure that it can demonstrate a valid solution. The student then simply tries to solve all scenarios posed by the teacher. Both policies interact and improve together, learning to generate and solve more and more scenarios of increasing difficulty. Below, we show several qualitative examples of scenarios that arise throughout training. After training, the student learns a more realistic and robust policy compared to baselines. We show some qualitative examples. Colored actors are controlled and gray actors are replayed. Here we see a collision exhibited by the baseline, whereas our model shows better interaction reasoning by having the blue car wait for the green car. In this example, the baseline orange car is too indecisive, whereas our model learns that it should make the turn as it has already entered the intersection. Here, the baseline pulls too far forward into the crosswalk, leading to a collision with the pedestrian. In contrast, our model has learned that the orange car should instead stop earlier. We've shown that asymmetric self-play training leads to a more realistic and robust student. Next, we evaluate the teacher's ability to zero-shot generate scenarios for other policies. This allows us to efficiently train the teacher at scale in lightweight simulation before deploying it to interact with and improve an end-to-end policy using high-fidelity sensor simulation. By training on data generated with our teacher policy, the resulting autonomy policy is also more robust. Here we show an autonomy model that was trained only on real data, evaluated on a safety-critical scenario where an actor does a cut-in. The baseline model does not react early enough, resulting in a rear-end collision. In contrast, models trained on teacher-generated scenarios have had more exposure to this type of scenario, and so the policy has learned to react and avoid the collision. This is another example of a scenario where there's a long-range stationary actor. The baseline model reacts too late and thus cannot stop in time, leading to a collision. In contrast, our approach has learned that in order to stop in time and avoid the collision, it must respond immediately. In this nominal merge scenario from the highway set, we see the baseline maintain speed and slightly tailgate the actor. For our approach, we see the policy slightly slow down to allow the merging actor in, displaying a subtle but more courteous maneuver. Thanks for watching. For more results and analysis, please see our paper.